In the previous lesson, we discussed how we could use the first derivative to find intervals that are increasing or decreasing, and how we could also use the first derivative to find local maxes and mins. So in this lesson, now we're going to bump that idea up to the second derivative. What can we learn about the behavior of the function from the second derivative? When we find the second derivative, and we find the critical values, meaning where the second derivative is equal to 0 or undefined. And we create a sign chart for the second derivative, just as we did with the first. The intervals where we have positive values on the sign chart will indicate where the function is concave up, and negatives will tell us where the function is concave down. So here's the official definition for the second derivative test. It says if a function f of x is such that the first derivative and the second derivative exists and can be computed, and we have a critical number c for f, if that critical value, when you plug it into the second derivative, falls on an interval where the second derivative is positive, f has a relative or a local minimum at that critical value c. So that value has to be a minimum. And then the same idea for when the second derivative is negative. If the critical value falls on an interval that is negative, that means the function on that interval is concave down. So here's our picture, which means that critical value would have to be a local max. Now, if the second derivative is 0 or undefined, the test fails and cannot be used to obtain information about the local max or the local min. So I have two examples that we're going to go through. I have one that's fairly easy and pretty typical. And then I have the next example as one that's a little bit more challenging. Okay, so we have this polynomial function, f of x is equal to 0.25x minus x to the third plus 3x minus 1. So here's our function. We want to use the second derivative test to come up with some information about the behavior of the graph. I need to find the first and the second derivative here. When I find the first derivative, I have x to the third minus 3x squared plus 3. So I need to find my critical values by looking to see what makes the first derivative 0 or undefined. Because the derivative is a polynomial function, there aren't going to be any values of x, so that it is undefined. So we don't have any asymptotes or holes in the graph. We find the values of x, which make the derivative equal to 0. We're going to get three values. So we would get negative 0.88, we would get 1.35, and we would get 2.53. Now these values are rounded, so they're not exact values, but I just rounded to two places. So these are the values that are going to make the derivative equal to 0. Now let's find the second derivative. So I'm going to take the derivative of the derivative. When I find the second derivative, I get 3x squared minus 6x. Now I'm going to find the critical values for the second derivative because we're going to use those to create our sign chart. So when I factor this and I solve for x, I'm going to get 0 and 2. So that's what I'm going to use to split up the intervals on my sign chart for the second derivative. So I put 0 and 2 on my sign chart. Above each of those, I put a little 0, so I know that that's what makes the second derivative 0. And then I pick test points for each interval. So on this interval here that's less than 0, I pick negative 1. And so when I plugged in negative 1 into the second derivative, I got 9, which is a positive number. So that tells me that this interval from negative infinity to 0, open interval, I'm going to put positives here on that interval, and that tells me that the function is concave up on that interval. Now, if I pick a value between 0 and 2, for this interval, I picked 1 here. When I plugged in 1 into the second derivative, I got that the answer is negative 3, and that means that on this interval here, it's going to be concave down. So I'm putting negatives here, and it's just my preference to show the smile or the frown shape. Then on the interval that's greater than 2, I used 3 as my test point, and I plugged it in, and I got positive 9, which means on this interval here, we're concave up. Now, if you look at the sign chart, at this point here, x0, it changes from concave up to concave down on either side. So it's positive on the left, negative on the right. So that means x is equal to 0 is an inflection point, and that tells us where it changes concavity. If I look at x is equal to 2 on this sign chart, it does the same thing. I go from concave down on the left to concave up on the right. So that means since it changes concavity, that means x is equal to 2 is also an inflection point. So these two are both inflection points. Now let's use the second derivative test to figure out if our critical values from the first derivative represents a relative max or a relative min. So my first critical value that I'm going to check, that's x is negative 0.88. Negative 0.88 falls on this interval here, the interval on the left. So because that's on an interval where it's concave up, this value of x has to be located at the relative min because it's the bottom of a valley. If I check x is equal to 1.35, that would be this interval here between 0 and 2. This is on an interval that's concave down, which means that x is equal to 1.35 has to be the x-coordinate of a relative max because it's going to be the top of a hill. And then the last, let's see, 2.53, that's our last critical value to check. 2.53 lies on this interval here, this concave up, which means this x right here represents the x-coordinate of a relative min. Now, of course, if we want to find actual vertical distance from the x-axis, we would have to plug in these values and find the corresponding values of y. And we would have to plug that into the original function. So now looking at the function and its derivative, here's the original function. Here's the second derivative. When we look at the original function, we had inflection points at 0 and at 2. And if you look here, here's one inflection point at 0. Here's x is equal to 0. And then here's another inflection point right here at x is equal to 2. So you can see that if I trace the graph, this is concave up. And then right about here is where it starts to turn concave down. And then at 2, it turns to concave up again. So those are definitely inflection points, and you can see that on the graph. Now, let's also verify that our local maxes and mins that we found on the previous slide are correct. We said that at x is equal to negative 0.88, rounded, by the way, don't forget, that would be a local min because that falls on an interval that's concave up. Then the next point we had was 1.35. If I come across and look at 1.35, that's right about here. And we said that 1.35 fell on an interval that was concave down and therefore had to be a local max. And you can see right here. And then the next one was positive 2.53. So that's right here. And the positive 2.53 fell on an interval that was concave up. So that would have to be a local min. If we look and compare this to the second derivative tells us where the function is concave up and concave down. If the second derivative is positive, that means it's concave up. So if I look at the graph of the second derivative and where the values of the second derivative are positive, That's going to be where the function is concave up. So the second derivative is positive, meaning above the x-axis right here. So that's from minus infinity up to 0. And we can verify that here when we look at the function. It's concave up from minus infinity up to 0. When we look at the second derivative, when it's negative, meaning it falls below the x-axis, those values are negative, which means on the function, that's going to be where the function is concaved down. So this is telling us between 0 and 2 on the function is going to be concave down. So if you look, between 0 and 2 is concave down. Now, because the second derivative is positive from 2 to infinity, that's where it's above the x-axis, that means on the function on the interval from 2 to infinity, that's where you're going to have that the function is concave up. So if we look at the function at 2 to infinity, that's definitely concave up. Now, the values of x that break it up from concave up to concave down and vice versa, that's when it's neither positive nor negative. That's when it's 0. That's your inflection point. So when we look at the graph of the second derivative, it's 0 at 0 and 2. So this means if I trace this left to right, on the graph of the function from here to here, this interval here, it will be concave up because it's positive. Then it hits this 0 here and turns to concave down on this interval from -2, from 0 to 2. So that means this right here, where it crosses the x-axis, for the second derivative, that's going to be your points of inflection on the function. So now we're looking at this area. This is where the function is negative. Here it hits 0 and then it changes to positive. So here is concave down on the function, and then here on this interval is concave up on the function, which means 2 is also an inflection point, changing from negative to positive for the concavity. So 2, if we look over here, that's our inflection point. It changes from concave down to concave up. Let's look at our second example. It's a little bit more challenging. We have the function 0.25 x to the third minus 2x squared plus 5.25x minus 4.5, all divided by x squared minus 1. When we take the first derivative, I'll let you guys do this for practice, but when you take the first derivative and you simplify it, you're going to get 0.25x to the fourth minus 6x squared plus 13x minus 5.25. And then that's all over, using the quotient rule, that's all over x squared minus 1 squared. So in order to find the critical values for our first derivative, we need to see where the first derivative is either undefined or equivalent to 0. We can clearly see that it's going to be undefined when x is either negative or positive 1. That's when we would get 0 in the denominator. So when the first derivative is undefined, we have plus or minus 1. So this is starting our list of critical values for the first derivative. Now, to see where the first derivative is equal to 0, I'm going to set the numerator equal to 0. And as long as it's not 1 or -1, where the top and the bottom would both be 0 at the same time, all we have to worry about is finding what makes the top 0, because 0 over anything, with the exception of 0, is just going to be 0. So if you set the numerator equal to 0 and you solve, we're going to get, these are rounded values. I got -5.8, 0.53, 2.26, and 3. So these values here is what makes the first derivative 0. Now let's find the second derivative. When you take the derivative of the derivative, again, I'll let you do the intermediate steps so you can practice. But when you find the second derivative and you simplify it, you're going to get 11x to the third minus 39x squared plus 33x minus 13, and then that's all over x squared minus 1 all cubed. So now to find our critical values for the second derivative, so we can use them to make our sign chart for the second derivative, what makes the denominator 0 is going to be where we have critical values so that the derivative is undefined, or the second derivative, I should say. And again, that's going to be plus or minus 1. And then if we look to see what makes the numerator 0, we want to make sure that it's not plus or minus 1 again, because we don't want 0 over 0. But other than that exception, we want to look to see what makes the numerator 0. For this cubic, we're going to get 3 roots. 2 of them are imaginary, and we only have 1 real root, and that's x is equal to 2.55. Since we're graphing on the real plane, we're not going to worry about roots that are complex. So our only critical value that makes the second derivative 0, that's a real number, is 2.55. So I'm going to use plus or minus 1 and 2.55 to make my sign chart. So, and then at plus or minus 1, that's where it's undefined. And then at 2.55, that's where it's equal to 0. So I put a 0 up here. So now we just have to get some test points and plug it into the second derivative. So on this first interval here, where it's less than -1, I picked -2. And when I plugged that into the second derivative, I got -11.96. So that means on this interval here, it's going to be concave down. On the next interval, that's between -1 and 1, I picked the test point 0. So for the test point between -1 and 1, I chose 0. And when I plugged that into the second derivative, I got 13. So that means on this interval between -1 and 1, it's going to be concave up. The next test point I picked was 2. Plug that into the second derivative, and I got -0.56. Again, these are rounded values. So that means on this interval here between -1 and 2.55, that interval for the function is going to be concave down. And then for the last interval here, I picked the test value 3, and that gave me a positive value, which means that interval is going to be concave up. Now, when I look at this sign chart, I only see one point that's considered an inflection point. That's this one right here, because it's equal to 0 and it changes concavity. It goes from concave down to concave up. For these two values here, it does change from concave down to concave up and vice versa here, but we have asymptotes at -1 and 1. So these are not going to be actual points on the graph that we can label as inflection points. These are actually asymptotes. So our only point of inflection here is 2.55. Now, using the critical values from the first derivative, when I start plugging those in and testing, I can find where I have my local maxes and mins based on the second derivative test, where we're looking to see where the interval is concave up and concave down. So looking at the critical values -5.8 and 2.26, those are on intervals that is concave down. So that would be this interval here. And let's see, this interval here. So those are going to be local maxes. Then for these two values, for 0.53 and 3, those fall on intervals that are concave up. So that means it's going to be a local min. It's going to be the bottom of a valley. Now let's look at the function and its second derivative. So for the pictures of the function and the second derivative, I blew this section up and this section up here so that you could get a better look at it, because when you're not zoomed in, it's really hard to see the behavior. So we said that for the graph of the function, we had that it's concave down on the interval from -infinity up to -1. So here's -1 right here, where we have a vertical asymptote, where you see my laser pointer right here. So from minus infinity up to that asymptote is concave down. Then we also said it was concave down between 1 and 2.55. So that's this here. And then, so this is where I blew it up for you, so it's hard to see what's going on. And so here it's concave down. And then we said it's concave up on the interval between -1 and 1. So that's this piece here of our rational function. We have our second vertical asymptote right here where you see my laser pointer. That's at 1, x is equal to 1. And then we said it was also concave up from 2.5 to infinity. So at this point right here, that's in here, it starts to flip back up again. It's really hard to see it unless you blow it up. But this part right here, even though it opens up real slow, it's still concave up at this point. So looking at where the second derivative is above and below the x-axis, that's where you can see that it's concave up or concave down. So when you look at this piece right here, that is positive. So that means on the graph over here, that's where it's going to be concave up. For this piece right here, this is all, it's hard to see. I should have blown this part up too, but this is all below the x-axis. It's getting really, really close. We have a horizontal asymptote there, but it doesn't actually cross the x-axis. So this is all negative from minus infinity to -1. So that means on the function, since this piece is negative, it's going to be concave down on the original function. When we look at this point here from, what was it? I think it was 2.55. Let me go back and look. No, it was 2.26. So this point right here, it's below the x-axis. So from here to here, since it's negative on the graph of the second derivative, that means it's going to be concave down over here. So that's this piece here. And then it starts to turn back up. And then when you blow it up, you'll see that from 2.26, it goes above the x-axis and then it flattens out so that, again, it's running along that horizontal asymptote, but it doesn't touch the x-axis again. So all of this piece from here and over is positive on the second derivative, which means on the function, that interval is going to be concave up. Okay, so for technology, the book uses this Wolfram alpha. I'm not a big fan of it. I think it's more of a preference. But I'm going to show you how you can find the derivative and second derivative on GeoGebra so you can check your work. Let's use that example that's on the technology slide. So we have 0.25 x to the fourth minus 2x to the third minus a half x squared plus 30. Okay, so I've adjusted the window so that we can see the basic shape of the function. If I want to find the derivative of this polynomial f of x, I can just hit f prime and it will show me the graph of the derivative. If you have trouble with it only showing the graph and not showing the equation for you, one thing that I have found is it's a little bit finicky when you're on just the regular graphing calculator. Sometimes this equation doesn't show up. But if you move to the 3D calculator and you put it in and you do the work here, for sure it will show up there. But I have seen where it's finicky and sometimes this equation doesn't pop up. Now, if I want to find the second derivative, I just hit F double prime. And then it shows me the second derivative in the graph. And you can see that it's color coded too. So the second derivative here is in blue. The first derivative is in orange and the original function is in red. If you're like me and you have bad eyesight and the red and the orange are pretty similar and you're having a hard time distinguishing the difference between the two, you can actually change the colors by coming up here to the dots. If you right click on it and you go to settings, up here, you can pick the color you want. So I'm going to pick a color that's different than like a red or an orange. I'm going to pick green. That's my favorite color. Okay, so now that I have it changed to green, and you can see the difference in all the functions here. Another thing that you can do, if looking at all three of these at the same time is a little bit overwhelming and you just want to look two at a time, whichever one you don't want to see at that moment, you can just click on this and it will hide it. So it will keep your work here, but it will hide it from the graph. So maybe I just want to look at the second derivative, or maybe I just want to look at the first derivative. Okay, so you can use these to either make it visible or hide it. One last thing that I want to show you that I think is really helpful. I'm going to use this as an example. We all know that pi has infinite digits, but let's say you're doing some kind of arithmetic and you want to keep as many of the digits as you can without having to retype all of them. GeoGebra set that equal to b. I can just tell GeoGebra to find f prime of b, and it puts in all those digits for me without me having to retype all of them. So think of this as a stored value.